Okay, so move on to the second example, third example, but the second one for today. Tom, you missed the first one, but you're just in time to see the beginning of the second one. So you'll see that one through. And again, I've got the video, so we'll be able to talk about that. This one's much shorter, so this one should go fairly quickly. Okay, so it says the height of a ball. So Jake will be happy because this one does not want to defy gravity. This one's going to work in a normal human world. So it says the height of a ball thrown in the air is given by x equals 5t times 4 minus t, where x is in meters and t is in seconds. Show that its acceleration is a constant function and sketch its graph. Okay, so the first thing we need to do, is not use our pencil upside down. I'm just going to give them both a little bit of a sharpen again. Okay, so show the acceleration is a constant function and sketch its graph. So we're going to start with x. Now, to find the acceleration, we're going to obviously have to differentiate twice on the second derivative. If you have a look at this function, at the moment it's set up like you'd have to do the product rule, but that would be really silly because if you have a look, this is just merely that. So please try, the only time you're going to have to use the product rule is if this was some power up here as well. Okay, so now if we look at velocity, which is the first derivative, I get 20 minus 10t, and the acceleration, we get x double dot is just going to be minus t. So we've found the acceleration. Let's go back and see what the question wanted us to do with it. And it says show that the acceleration is a constant function, okay? So let's have a look at the acceleration. It's negative 10. There's nothing to do with t there. So this is constant, right? You have no t in there. It can't change in any way. It is, the acceleration is just negative 10. And in fact, again, Jake, you'll be happy. It's the rounded off version, but it's like your acceleration due to gravity, which is at negative 9.8 meters per second squared. And we've got it here rounded off to negative 10 for this particular function, okay? So the second part then says sketch the graph. So this is a tough one. Now we're dealing again with the acceleration being negative. So I'm going to have the majority of my function with the negative section being visible. So if I go 0 here, negative 2, negative 4, negative 6, oh, I've made it a bit big, negative 8, negative 10, the entire acceleration from 0, and I can't go beyond because I can't have time being negative, that's your acceleration, just that straight line, okay? And that's showing that it's constant. Of course, you're all going to use a ruler, aren't you, when you do it in an exam?
Yeah, totally.
But you are. All right. So last part was determine the values of t for which the ball is speeding up and for which it is slowing down. So what I want to do is just, first of all, have a little bit of understanding going on under here, which is not the official part of the solution. But if we go back to the original function, we had x equals 20t minus 5t squared, okay? So if I drew a displacement graph, So there's X and T. Now at the moment, I've also got the negative version on the other side there just to get that parabola going. But obviously, we will be only genuinely starting with T 0 or greater. So if I try to sketch that, I'd factorize and I'd have that was 5t outside of, the original version, right? 4 minus t. So it's going to pass through at 0 and it's going to pass through at 4. T equals 4. But it's a negative, so it's concave down like that. And remember, we're not going to use that section there. We're just going to have this section here. Okay. So that also makes sense for a ball. You throw it up in the air, it goes up to its maximum height, turns around, and now it's coming back down. Okay. Does the question talk about thrown in the air? Okay. What's the other problem with my graph at the moment?
Does it go past the point where you threw it from?
Go past the what, sorry, Ben?
The point where you threw it from, like the origin.
It does.
Going down a hole.
Yeah, if that's my point where I threw it from, that would be, I guess, okay if I'm, taking it as me standing and throwing it from 1.5 meters above the ground or something like that. Then if that is my origin point, then yeah, I could come down here. But if this is ground level, I've got an issue where I've got some sort of powerful ball that's going to go down under the ground. Okay. Yeah. So whenever we're dealing with these kinds of questions, we just need to consider what those conditions are as to how we draw it. Because normally if we had somebody standing and holding the ball, we treat it as the point from which they left the ball, say 1.5 meters, and draw it like that. So just consider the conditions that they give you when you do get to the point of sketching some of these graphs, and look at the limitations of the models and whether or not you can draw this going below. Okay. This is not actually part of the question. This is just giving you guys the understanding. But the question's asking for us to explain where and why the ball can speed up and slow down if the acceleration is constant. So this is this understanding I was talking about in terms of looking at whether the acceleration is working in the same direction as the velocity or whether it's working against the velocity. So if you think about it, when I first of all, now that's the graph of displacement over time, but what they're saying the ball is actually doing is being pitched vertically up, and then it's going to come back down to the ground. Right, so we're still talking about that motion in one direction only, in a straight line. But over time, we're saying after 1 second, the ball was now so many meters above the ground. After 2 seconds, another so many meters above the ground, etc. So that's plotting it over time. The actual ball is going to look like it's moving like this. Okay, so it starts moving up, but our acceleration, which is constant, is negative and pushing down. So what's it going to do to the particle as this is going up? It's going to move against it and slow it down until it gets to the point where the particle slows to the point where for that initial moment it's stationary. Sorry, instant rather than initial. For that instant moment, it's stationary, turns around, and then moves downwards. Okay, because and that -10, as we've seen, is like gravity working against it. So the ball's heading up into the air, gravity's working against it, slows it to the point where for an instant it's stationary, turns around, and now it starts to move down. So once it's going down and it's got gravity working with it, or the acceleration of -10, then now, despite acceleration still being negative, they're now going in the same direction. Velocity and acceleration are negative, and therefore it will speed up in that negative direction. Okay? Is there anybody who wants to ask a question before I actually look at how we answer the question properly. Do people understand what we're talking about now, where we've got to really consider the direction of the velocity and the direction of the acceleration as to whether or not we can say it's slowing down or speeding up? Can people give thumbs up or give me a sign? Anything? Hang on. Okay, I can see some thumbs up. Are there any thumbs down by anybody?
You can't do a thumbs down.
I've got a clap from Jake. Thank you, Jake. You're happy to see the acceleration in there, are you? The gravity in there, Jake? Okay. All right. I'll move on then. So let's actually answer the question. So it says, determine values of t for which the ball is speeding up and for which it is slowing down. So from what we've just looked at, are you happy to see that it's actually going to be slowing down and then speeding up at the end? So the first part's going to be slowing down, the second part's going to be speeding up. And it's going to slow down until its turning point. So do we know when the particle turns at this stage?
T equals 2.
And how did you work that out?
Because it's halfway between its two intercepts.
Right. So because we've drawn the parabola, we all know that that turning point for a parabola is going to be in the middle between 0 and 4. And so it would go then at t equals 2. Okay. But let me do it from an algebraic point of view and imagine that, you know, we hadn't done all that sort of stuff. And so we were doing it from a different point of view, or perhaps it was a graph we couldn't sketch necessarily straight up. So which value are we ultimately looking for when we want to know that value there? What are we what's the name of the thing we're looking for?
Maxima.
Right, the maximum turning point. Okay, so to find the maximum turning point, because at this stage we've got our functions from, sorry, I'm just getting them back from the previous page. So we knew that our displacement was 20t minus 5t squared. We knew our velocity was 20 minus 10t, and we knew our acceleration was constant at minus t. Okay, so if we want to find the maximum value, then we want to solve where the first derivative or velocity is 0. Okay, so the ball will be maximum, which means it's going to turn when the velocity is 0. Oh, Betty's trying to come in. Okay. And so we're going to be solving 20 minus 10t equal to 0, velocity equal to 0. So you get 10t equals 20 and you get t equals 2, which is what Sam said a moment ago. Okay, so that matches. All right, so we know that therefore ball reaches maximum at 2 seconds. Okay, now what if they asked you to also tell us where that happened or at what height that happened? What
You sub in 2 seconds into the x.
Right, because remember, x is representing this vertical component, how high. It's not our usual x this way. So you'd substitute your t equals 2 seconds into our expression for x, and that would tell us how high up the ball reached at that turning point. So you'd go the 20 minus 2 is 40, and minus 5 times 4 is 20. So it's going to reach 20 metres above the ground, okay, at its maximum. But they haven't actually asked us for that, have they? No. Okay. So we know that it's going to be slowing down up until it reaches its maximum turning point, and then it's going to be speeding up after that, okay? So the values of t, it's going to be slowing down. Now, therefore, we want our t value to be less than 2. Can it equal 2?
Yes.
Is it slowing down there, or is it stationary there for just that?
Stationary.
Don't make it equal to 2. It's less than 2. All right. Do I need anything on the other side? Is it just less than 2?
Time can't be negative.
Right. So we're going to have to start at 0. But can it equal 0?
Yes.
Yeah. I mean, I guess if you were to be technical with it, you're saying at that instant that you release the ball, it can't be slowing down. But I would suggest, yes, you're including that, because you're saying it can equal that value for t equals 0, and it starts to slow down immediately. Okay. All right. And where is it speeding up? It's
T greater than 2.
once it's turned and it's going that way, yeah. Okay. Now, this question hasn't taken us as far, and it gets more when we get into projectile motion again. There's going to be a point at which we do hit the ground. This question hasn't specified when we hit the ground, which is why, remember, I said to you, this sort of area here is a bit grey. Did we start actually throwing the ball from above the ground, and therefore you can go a bit below the axis and that sort of stuff? And they haven't asked us to sketch any of this. But if they gave us some initial information about where the ball started above the ground, or if the ball started at ground level, then we would also have to include the fact that not only would it be greater than 2 seconds, but we'd have to stop when it hits the ground. So in our case, say the ground was at the same height as where you left the ball, then we know that we got back down to the ground after 4 seconds. So we'd have to stop that part there at 4 seconds. But that's not, that's kind of going beyond this question, because they haven't specified anything about the ground. Okay. So it then says explain why this can happen when the acceleration is constant. So what are we going to do? How are we going to describe that? Anybody? Anybody got an idea of how we would describe how it can slow down and speed up if the acceleration is constant? Because you're the ones who are going to be stuck in an assessment situation having to put this down. So I don't want to just say the answer.
Initially, the speed is in the opposite direction to the acceleration.
Yeah. But don't use the word speed, because speed, remember, doesn't have direction. So make sure you use that word velocity. Okay. So we're going to have to be careful with that terminology, but yeah, you're exactly right. Initially, oh, my hand's massive. Initially, the velocity is heading up as positive, the acceleration is negative, and the acceleration continues to be -10, but that's going to slow that particle down till it stops, turns around, and then they're going to come down together and start to speed up because they're working in the same direction. Okay, so our explanation, now I wrote this out earlier so that I would make sure I had it worded nicely, but I said in the first 2 seconds, the ball is moving with a positive velocity, and heading up. but the acceleration is acting against it. And slowing it down. After turning, the ball is moving in the same direction as the acceleration. And so speeds up. And before I publish this, I'll tidy up that bit there and make that nicer there for you so that you can see that. Okay. So, any clarifying questions? Tom, are you still with us?
Yeah, I'm here.
Okay, so you missed the first one, but did you understand, you know how you were asking yesterday about some of that acceleration stuff and not quite understanding how they move in the same and different directions? Did you get a better understanding with this?
Yeah, I did.
Yeah?
And also, I watched a video on it yesterday, just explaining it. So.
Okay, all right. Anybody else? So we all good? All right, so I have already posted on the Google Classroom the questions that I want you guys to have a look at. So use the remaining time from this period to now, try and get stuck into some of those. Monday, I'll give us some work on exponential growth and decay. It used to be something that was in the advanced course, but now they've moved both components into the extension course, so there was a harder version in the extension. And again, when we were doing rates of change, we actually did some exponential growth and decay questions within just normal rates. We just didn't specify that they were exponential growth and decay. So there's going to be some stuff coming up next week that will be quite familiar and quite nice. Okay. Next week also, I will be starting the advanced work. So I've still got a couple of lessons to go on this. I'm going to actually divide up advanced and extension for a little bit and do the extension effectively whenever we would have had period 0 classes, and I'll do the advanced in the normal advanced time slots and get those going. So we'll have a couple of things going at the same time just for a little bit, and then we'll get back onto one thing at a time after that. Any questions before we wrap it up?
Miss?
Yeah.
At the end you've written the last sentence, it says, as the acceleration something so speeds up.
Oh, no, it makes sense. After turning, the ball is moving in the same direction as the acceleration and so speeds up.
And it's what speeds up? Oh, right, I get it.
Yeah?
Yeah. Thank you.
Anyone else? It's good to know that you guys are still struggling with my writing.